Hi, my name is Bill, and this is a quick introduction to my project NFNet, which stands for Non-Interacting Fermion Simulation Network. This is a work that has strong theoretical and practical values, as I will show later in this video. Here are the main sections in this slideshow. When it comes to efficient classical simulation of quantum systems, the one thing that will pop up in the minds of most people would be, given a circuit setting, how to classically simulate a quantum circuit, where you input a state that is easy to prepare, measuring some qubits at the end, and the output bit strings, spin up or spin downs, will strictly follow probabilities determined by the specific parameters that this quantum system has. So now, looking at a broader scenario where we want to classically simulate any quantum system, which is most likely continuous by nature, that goes beyond the setting of the one-dimensional circuit. Given an initial state of the system and a parameterized Hamiltonian, we wish to know what the system readouts will be and their probabilities. After some time evolution. Why is this crucial? If we take a look at quantum science in general, researchers always wanted to figure out the exotic properties and behaviors of a plethora of quantum systems at the very large scale, such as Rayburg atom arrays, graphene, two-dimensional quantum materials, quantum optics, and etc. Most importantly, numerical simulations of these systems is the only accurate path to systematically testify the theoretical findings, especially when the hardware system themselves are subject to noise, measurement errors, and scalability issues. In one word, how will we know a system will behave at the super large scale if this large system cannot even be stably built or run to begin with? Only large-scale numerical simulations can help us better understand and explore these quantum behaviors, which is otherwise intractable. And here is a broad summary of the task at hand. And again, I want to emphasize that this classical simulation problem is not just restricted to the one-dimensional quantum circuit setting, and that there are many other interesting systems characterized by continuous Hamiltonian interactions as listed here. Some known classical methods that simulate quantum system efficiently are the Clifford groups simulation, which is in a quantum circuit setting, matrix product states, which gets rid of minor entanglement bond dimensions to reduce the size of the vector, and 3, match gate simulations and its free fermion formalism, both originally proposed in the quantum circuit setting. Here I have a brief summary of the pros and cons of these methods. For Clifford and matrix product states, one can only approximate a Hamiltonian via some variation of the Trotter decomposition to some precision. And in addition, Clifford groups does not have continuous control parameters, which is its biggest shortcoming. On the other hand, the match gate / free fermion method, which is used in my NFNet, can model exact, continuous, and long-term dynamics characterized by allowable Hamiltonian structures, which I will talk about later. So our theoretical foundations largely build upon the amazing works of Professor Leslie Valiant, who first proposed the match-gate simulation idea, and Professor Barbara Terhel, who came up with a systematic mapping of the match gates into free fermion interactions, i.e., quadratic in the creator and annihilation creators. Our novelties of the NFNet include both implementational and theoretical aspects. Implementationally, I have developed a PyTorch package that does the computation of quantum system readout probabilities given a set of continuous control parameters, which supports batch processing and autogradient calculations. Theoretically, in my manuscript, I have also added detailed derivations of the free fermion simulation on cases including non-nearest neighbor fermion mode interactions, dense Hamiltonians that go beyond the one-dimensional quantum circuit gate construction, and also some special cases of long-range non-local interaction Hamiltonians. And for more information, please refer to my manuscript posted to arXiv. So what exactly is NFNet? Well, the previous studies have shown that these three special Hamiltonians are building blocks to interactions that can be classically simulated in polynomial time. In the most simple case, they are acting on nearest neighbors, for example, as shown here. These three Hamiltonians are mapped into fermion creation and annihilation operators. Again, here I'm just showing the simplest case where these interactions are acting on nearest neighbor fermion site, but that is not the restriction. So what does my NFNet do computationally? At the back end of NFNet, it is carrying out a procedure as described here. When we start from a fermionic mapping, given a special Hamiltonian construction, in order to compute the output probability of observing some bit string readout y, given a x input bit string, a series of complicated matrix decomposition and multiplications are done classically through the PyTorch matrix operations in parallel. And at the same time, the gradient of the output probability with respect to the Hamiltonian parameters theta are computed via the PyTorch autogradient function for later updates of the system. And the computational complexity of this computation scales in big O n to the 3, because it involves the computation of determinants, which is still in polynomial time. However, NFNet does not merely end here. In my manuscript and implementation, I have extended the interactions to non-nearest neighbor fermion modes, which I have shown rigorously corresponds to a dense Hamiltonian construction composed of arbitrary pairwise interactions Hij, where each Hij can act on non-nearest neighbor fermion modes, and it's shown here. Well, please note that these Hamiltonians go beyond what a quantum circuit can model through gate composition, because each of these Hij generally does not commute with each other. Here you see the A, B, C, D, all the way to F coefficients are real continuous parameters corresponding to how long we want to evolve the quantum system for. Therefore, you see NFNet supports accurate long-term Hamiltonian evolutions, where the computation complexity does not depend on how long we want to evolve the system for, which, however, is not the case for other methods, such as the matrix product states or the Clifford simulations. Before I go over to the demonstrations, I want to quickly talk about the current state of development of NFNet. I have an open source base code ready and debugged, and I have finished the paper that documents the theoretical foundations. I've also coded up some interactive tutorials written in Jupyter Notebook to show users how to set up NFNet and how to run some numerical experiments on it. The reason that I apply for the Unitary Fund is that there are many, many things to be done, and I wish to extend my platform to its fullest potential through website building, code optimization, more academic research, and networking, both academically and industrially. Now I will show you what I have done theoretically and implementationally. First, we have a paper with all of the theoretical foundations documented. Building on top of the work of Professor Terhal, we derived the Fermion to Pauli correspondence, the non-nearest neighbor Fermion interaction structure, and its underlying control parameters. Here is a section of the paper where I described how to set up a NF network with user-defined connections. And how to interact with the NF network and play around with its parameters. The plot here at the corner shows the output probability calculation of the NFNet versus exact diagonalization on a 10 qubit deep circuit. These probability outcomes completely agree with each other to allowable precision. Here is a screenshot of the Jupyter Notebook tutorial where I compare the runtime of modeling a given Hamiltonian via NFNet and via exact diagonalization. As you can see here, NFNet has a clear advantage in terms of speed. The numerical difference measured in total variance between the NFNet and exact diagonalization are around the order of 1 million. NFNet also comes prepackaged with variational quantum algorithms use cases such as generative Bohr machine, solving the max cut problem, etc. This is another screenshot of my tutorial on solving the max cut problem, where the graph is fully connected with weighted edges. And NFNet is able to compute everything super fast and is able to find the optimal solution of this graph. This is another example of the generative Bohr machine, where the goal is to train the quantum system such that its output probability distribution is close to a target. In this case, my quote-unquote probability distribution is a grayscale MNIST digit 0. And the Fermion system is actually able to learn this distribution within a reasonable amount of iterations. More mind-blowingly, on a super large scale setting, namely with 196 qubit that models any binary 14 pixel by 14 pixel image, NFNet can efficiently conduct a pattern recognition task, namely how to train the network such that the probability of outputting this given pattern 9 will be maximized. NFNet handles this case very, very well and the training is done in a matter of minutes with great output probabilities. Even more mind-blowingly, to further demonstrate the power of NFNet, in my research, I conducted a 144-qubit binary classification task using binary MNIST digits. I built a quantum perceptron that is able to train on a dataset of 200 images of various digit 3 and digit 9s. Each image is 12 pixel by 12 pixel. Hence, I used a 144 qubit basis state to represent each classical image pattern. The training is done variationally, and the parameters are updated by gradient descent. This system setup naturally corresponds to the central spin time evolution of a Rayburg array, which gathers information of each surrounding node into a central node by long-range interactions, as modeled by the circuit here. And we finally measure the center spin multiple times to determine the predictive probability of an input image pattern, either belonging to class 9 or belonging to the class 3. Note that each image here is a classical bit string that is easy to prepare, and at each iteration, we input these bit strings one by one into the system. We evolve the system, and we measure the output node multiple times to get the output probability, compute the loss function, and then update the system parameters variationally. On the training and validation datasets, this 144 qubit system is actually able to learn very well. Here are some of the training plots and validation plots. Quite interestingly, we observe a sharp phase transition in the classification boundary during the training, which can be related to the unique quantum properties of the system. This concludes this presentation, and I have much more work to be done in this area. Thank you very much for watching this video. I hope you like my research and product. If you have any questions, please contact me through my email. Thank you very much.